Every single second of your life, you are locked in an invisible battle with the most pervasive physical phenomenon in the universe. It anchors the vast oceans to the planet, holds the Earth in its relentless orbit around the Sun, and binds billions of stars into majestic spinning galaxies across the cosmos. Yet, despite its overwhelming cosmic authority, gravity is by far the weakest fundamental force in all of physics. Think about that stunning contradiction for a moment. The gravitational pull of the entire Earth, a giant sphere weighing nearly 6 septillion kilograms, is currently working to pull your body toward its molten core. And yet, you can easily defeat the combined gravitational mass of our entire planet simply by lifting a single cup of coffee off your desk or picking up a paperclip with a tiny refrigerator magnet. The electromagnetic forces in that tiny magnet effortlessly overpower the gravitational draw of an entire world. This profound paradox is just the beginning of a far deeper mystery. We treat gravity as a settled fact of daily existence, a simple rule of down versus up that Sir Isaac Newton supposedly solved with a falling apple. But modern physics reveals a far stranger reality. What if gravity is not a force at all? What if everything you were taught about how objects attract one another is fundamentally flawed? Today we will explore gravity, the fundamental force we completely misunderstand, and uncover how our quest to define it has pushed human knowledge to the absolute edge of reality. If you want to journey with us through the cosmos, feel free to like this video and subscribe to the channel if you enjoy deep scientific explorations. Before we unravel the hidden architecture of space and time, please leave a comment below sharing where in the world you are watching from right now and what time it is wherever you are. To truly grasp how deeply we misinterpret gravity, we have to look back at how humanity first tried to make sense of why things fall. For thousands of years, our species accepted an explanation that felt completely intuitive, even though it was entirely wrong. The ancient Greek philosopher Aristotle taught that every element in the cosmos had a natural place where it inherently belonged. Earth and water belonged at the center of the universe, while air and fire belonged above. According to Aristotelian thought, a heavy stone falls to the ground not because an external force acts upon it, but because the stone is composed of heavy elements striving to return to their natural home at the center of the Earth. Furthermore, Aristotle claimed that heavier objects fall faster than lighter ones, asserting that a rock 10 times heavier than another would plummet 10 times faster through the air. Because this idea matched everyday casual observation, it stood virtually unquestioned for nearly 2,000 years. People saw a heavy brick hit the dirt long before a feather or a dry leaf drifted down, so they assumed Aristotle was correct. The flaw in this logic was that it confused the intrinsic property of weight with the resistance caused by the medium through which objects move, namely air. It was not until the late 16th century that the Italian polymath Galileo Galilei shattered this ancient dogma. Galileo realized that air resistance acts as a distorting variable. Through careful experimentation with inclined planes and thought experiments involving joined weights, he arrived at a revolutionary conclusion. In the absence of atmospheric drag, all objects accelerate toward the ground at the exact same rate, regardless of their mass or composition. If you drop a massive iron cannonball and a light wooden sphere simultaneously in a total vacuum, they will hit the floor at the exact same instant. Galileo measured this acceleration, demonstrating that gravity causes falling objects to speed up by approximately 9.8 meters per second during every second of fall near the surface of the Earth. Yet, while Galileo successfully mapped the kinematic behavior of falling bodies, he could not explain why this uniform acceleration occurred. He identified the pattern of motion, but the underlying physical mechanism remained entirely hidden in darkness. That crucial next step occurred in the 17th century through the genius of Sir Isaac Newton. Amid the Great Plague of London, while isolated at his family estate, Newton formulated a mathematical framework that unified the motion of earthly objects with the movements of celestial bodies. Legend tells of Newton watching an apple fall from a tree in his garden and wondering if the very same force drawing the apple toward the dirt might extend all the way out into the heavens to keep the moon in orbit around the Earth. Newton realized that the moon is not simply suspended motionless in space. nor is it driven forward by divine hands. Instead, the moon is perpetually falling toward the Earth. However, because it possesses a high forward tangential velocity, the surface of the Earth curves away beneath the moon at the exact same rate that the moon falls. The moon is in a continuous state of freefall, continually dropping around the curve of our world without ever hitting the ground. With this profound insight, Newton synthesized his universal law of gravitation. He published his findings in 1687 within his landmark treatise, the Philosophiae Naturalis Principia Mathematica. Newton declared that every particle of matter in the universe attracts every other particle of matter with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Mathematically, this meant that if you double the mass of an object, its gravitational pull doubles. But if you double the distance between two objects, their mutual gravitational pull does not merely halve, it drops to 1/4 of its original strength. If you triple the distance, the force weakens to 1/9. This inverse square law provided an astonishingly accurate tool for predicting the motions of planets, moons, comets, and cannonballs. With a single elegant equation, Newton swept away the ancient divide between the earthly realm and the heavenly realm. The same physical laws applied everywhere across the cosmos. Newton's mathematics worked with incredible precision. Astronomers used his equations to predict celestial movements, calculate ocean tides, and even discover new worlds. When subtle irregularities were observed in the orbit of Uranus, scientists applied Newton's law of gravitation to predict the existence, mass, and coordinates of an undiscovered planet whose gravity was pulling Uranus off course. In 1846, astronomers pointed their telescopes toward the exact coordinates predicted by these calculations and discovered Neptune. Newton's theory appeared to be an absolute, unshakable description of cosmic reality. Yet, despite its triumphs, Newton's theory contained a massive, unsettling flaw that haunted Newton himself. His mathematical model described how gravity behaves with remarkable exactness, but it utterly failed to explain what gravity actually is, or how it operates across vast expanses of empty space. According to Newtonian physics, gravity is an instantaneous force that acts at a distance. If you have two massive spheres placed light years apart in a vacuum, Newton's law dictates that they instantaneously exert a gravitational force on each other across that empty void, without any physical medium connecting them. Newton recognized the profound philosophical problem with this assumption. In a famous letter to the philosopher Richard Bentley, Newton admitted that the idea of inanimate brute matter operating upon other matter without mutual contact, through a vacuum, without the mediation of something else, was to him an absurdity so great that no person competent in scientific thinking could ever fall into it. This limitation came to be known as the problem of action at a distance. How could the Sun instantly pull on the Earth across 93 million miles of empty vacuum? If the Sun was suddenly wiped out of existence by some cosmic event, Newton's equations implied that the Earth would instantly lose its gravitational anchor and fly off in a straight line at that very microsecond. But how could physical information travel instantly, across millions of miles, with zero time delay? Furthermore, as observational astronomy grew more precise during the 19th century, small anomalies began to surface that Newton's inverse square law could not resolve. The most famous of these was the anomalous perihelion precession of Mercury. Mercury, the innermost planet in our solar system, orbits extremely close to the immense gravitational mass of the Sun. As it traces its elliptical orbit, the point of closest approach, known as the perihelion, slowly shifts or precesses over time due to the subtle gravitational tugs of the other planets. Astronomers meticulously calculated the expected rate of Mercury's precession using Newton's law of universal gravitation. But when they compared their theoretical predictions to actual telescope measurements, they discovered a persistent discrepancy. Mercury was precessing slightly faster than Newtonian physics allowed. The difference was tiny, roughly 43 arc-seconds per century, a fraction of a degree. Yet, in the rigorous world of celestial mechanics, that microscopic variance was a glaring signal that something was deeply wrong. At first, scientists assumed there must be an unseen planet orbiting even closer to the Sun, whose gravity was pulling Mercury off its predicted track, just as Neptune had pulled Uranus. They even gave this hypothetical inner world a name, Vulcan, and spent decades scanning the glare of the solar corona during total eclipses to find it. But Vulcan was never found because it did not exist. The failure to locate Vulcan highlighted a fundamental limitation in classical physics. Newton had provided humanity with a masterclass in accounting for gravity's effects, but he had built his framework upon a flawed foundation. He assumed that space was an absolute, rigid, unchanging backdrop, an empty stage upon which events occurred, and that time flowed at a uniform, unalterable rate everywhere in the universe. Newton's gravity was a mathematical abstraction, a force that operated magically across space without a medium, moving faster than any speed limit could allow. It was an extraordinarily useful approximation, accurate enough to land astronauts on the Moon centuries later, but it was not the complete truth. The true nature of gravity remained hidden, awaiting a complete conceptual revolution that would dissolve the notion of gravity as a traditional force altogether. To resolve the fundamental flaws of Newtonian physics, the world required a complete transformation in how we conceptualize the universe. That transformation arrived in the early 20th century through the mind of Albert Einstein. Einstein realized that to understand gravity, he had to challenge two of the most deeply ingrained assumptions in human history: the idea that space is an empty, rigid stage, and the belief that time flows at a constant rate for everyone everywhere. Einstein began with a simple yet profound realization that he later described as the happiest thought of his life. He imagined a person falling off the roof of a house. During the fall, if the person drops an object, that object floats alongside them in a state of weightlessness. To the falling observer, gravity has effectively vanished. Einstein recognized that there is no physical experiment an observer can perform in a closed room to distinguish between being in free fall within a gravitational field and floating weightlessly in deep space, far away from any massive bodies. Conversely, if you are inside a rocket accelerating through deep space at 9.8 meters per second squared, you feel an artificial weight pushing your feet into the floor that is completely indistinguishable from the downward pull of Earth's gravity. This insight is known as the equivalence principle. It revealed that acceleration and gravity are not merely similar, they are fundamentally the exact same physical phenomenon. But this equivalence raised a radical question. If a beam of light travels in a straight line across an accelerating rocket, an observer inside the rocket will see the light beam curve downward because the floor of the rocket is moving upward while the light travels. If acceleration bends light, then, by the equivalence principle, gravity must also bend light. However, light possesses no rest mass. Under classical Newtonian mechanics, a gravitational force acts upon mass. How could gravity pull on a beam of light if light has no mass to be pulled? Einstein's revolutionary answer was that gravity does not pull on light at all. Instead, gravity alters the very shape of the medium through which light travels. Gravity curves space itself. In 1915, after years of intense mathematical development, Einstein published his masterpiece, the theory of general relativity. In this framework, space and time are no longer separate, static backdrops. They are woven together into a dynamic, four-dimensional continuum called spacetime. Spacetime is not an empty void. It is a physical fabric that can stretch, bend, warp, and ripple in response to the presence of matter and energy. To visualize this, imagine a large, stretched rubber sheet held taut at the edges. If you place a heavy bowling ball in the center of the sheet, its weight causes a deep depression or well to form in the fabric. Now, if you roll a small marble across the sheet, the marble does not travel in a straight line. As it approaches the central depression, its path curves inward toward the bowling ball. If you throw the marble with just the right speed and angle, it will continuously roll around the slope of the depression, tracing an orbit around the bowling ball. The marble is not being pulled by an invisible, magical force radiating from the bowling ball. The bowling ball is simply warping the geometry of the rubber sheet, and the marble is merely following the straightest possible path through that curved surface. In four-dimensional geometry, these straightest possible paths through curved spacetime are known as geodesics. This is the central mechanism of general relativity, famously summarized by the physicist John Wheeler. Matter tells spacetime how to curve, and spacetime tells matter how to move. Under this view, gravity is not a traditional force pulling objects downward. Earth does not exert a pull on an apple hanging from a tree branch. Instead, the immense mass of the Earth curves the surrounding spacetime fabric. When the stem of the apple breaks, the apple does not get tugged toward the dirt by an invisible tether. The apple simply floats freely through a region of space that is falling inward toward the planet's core. What we perceive as weight or downward force while standing on the surface of the Earth is actually the solid ground pushing up against our feet, accelerating us upward and preventing us from following our natural geodesic path through curved spacetime. When you drop a stone from your hand, it is not accelerating downward because a force is dragging it down. The stone is in freefall, moving inertially through warped spacetime. You, standing on the ground, are the one experiencing a continuous upward acceleration because the electromagnetic forces between the atoms of the solid Earth are pushing against your shoes, forcing you out of your natural freefall path. This paradigm shift completely solved the theoretical problems that had plagued Isaac Newton. First, it eliminated the absurd concept of instantaneous action at a distance. If a massive body moves or changes position, it does not instantly affect every other object in the cosmos. Instead, changes in the shape of space-time travel outward as ripples through the fabric of space at a finite speed, the speed of light. If the sun were to suddenly disappear, the Earth would not immediately fly off into deep space. The curvature of space-time around the sun would flatten, and that change would propagate outward across 93 million miles of space as a wave. The Earth would continue to orbit smoothly in its curved pocket of spacetime for roughly 8 minutes and 20 seconds, the exact time it takes light to travel from the Sun to the Earth, before the gravitational wave reached our planet and freed it from its orbit. Second, general relativity provided a perfect, elegant solution to the mystery of Mercury's orbit. Because Mercury is extremely close to the gigantic mass of the Sun, it moves through a region of spacetime that is deeply curved. When Einstein applied his new field equations to calculate the path of Mercury through this severely warped region, his calculations yielded an extra shift in the planet's perihelion that matched the observed discrepancy of 43 arcseconds per century with exact accuracy. No hypothetical hidden planet named Vulcan was necessary. The anomaly was simply the signature of space itself being bent by the mass of the Sun. Despite its mathematical elegance, general relativity was such a radical departure from classical physics that many scientists remained skeptical. A theory that claimed space could bend and time could slow down required definitive empirical proof. That proof came in 1919 through an ambitious astronomical expedition led by the British astrophysicist Sir Arthur Eddington. Einstein's theory predicted that starlight passing close to the edge of the Sun would be deflected by the curved spacetime created by the Sun's immense mass. Under Newtonian calculations, light would either not bend at all or bend by only half the amount predicted by general relativity. However, observing stars near the Sun is normally impossible due to the overwhelming glare of daylight. The only way to test the prediction was during a total solar eclipse when the Moon blocks the solar disk and reveals the stars situated in the background sky. In May of 1919, Eddington travelled to the island of Principe off the coast of West Africa, while another team set up instruments in Sobral, Brazil. During the brief minutes of totality during the eclipse, they photographed the positions of stars located directly around the obscured Sun. When they compared those photographs with reference images taken of the same star field at night when the Sun was far away, the result was unambiguous. The presence of the Sun shifted the apparent positions of the stars by the precise angle predicted by Einstein's field equations. The announcement of these results shocked the scientific world and made Einstein an international icon. Space was not a rigid, empty void. It was a physical entity that could be bent by mass, altering the trajectory of light itself. General relativity also revealed that the warping of spacetime affects time just as deeply as it affects space. Because space and time are fundamentally bound together, regions of deep spacetime curvature cause time to pass more slowly relative to regions where spacetime is flat. This phenomenon is known as gravitational time dilation. Closer to a massive object, where the gravitational curvature is strongest, the flow of time slows down. A clock placed on the surface of the Earth ticks slightly slower than an identical clock placed in the vacuum of deep space far from any celestial body. While this effect on Earth is extraordinarily small, amounting to fractions of a microsecond per year, it is a physical reality that modern technology must account for every single day. Our modern Global Positioning System, or GPS, relies on a constellation of satellites orbiting roughly 20,000 kilometers above the Earth's surface. Because these satellites operate in a region where spacetime is significantly less warped than it is on the ground, their onboard atomic clocks tick faster than identical clocks on the surface by approximately 45 microseconds per day. Even after accounting for the special relativistic effect of their orbital speed, which slows their clocks down by 7 microseconds per day, there remains a net difference of 38 microseconds per day. If engineers did not continuously apply the mathematical corrections derived from Einstein's General Relativity, the distance calculations in your smartphone's navigation app would accumulate errors at a rate of nearly 11 kilometers every single day, rendering satellite navigation completely useless within minutes. Through general relativity, Einstein dismantled the classical illusion of gravity. Gravity is not an invisible, mysterious rope pulling objects across empty space. It is the geometric reality of a flexible, dynamic universe where mass shapes space, space directs mass, and time itself stretches and slows in the presence of matter. Yet, as revolutionary as this understanding was, it was only the beginning of an even deeper journey into how gravity shapes everything from the geology beneath our feet to the far edges of the observable universe. When we look at Earth from space, our planet appears as a perfectly smooth, shimmering marble floating serenely through the void. From that distance, it is easy to assume that the force of gravity operating across its surface is uniform, predictable, and unchanging. We speak of standard gravity as a constant acceleration of 9.8 meters per second squared, treating it as an absolute number in textbook physics. But reality is far more dynamic and uneven. In truth, Earth is not a perfect sphere, nor is its internal mass distributed evenly. As a result, the gravitational field beneath our feet is a complex, shifting landscape of invisible peaks and valleys. Because the Earth rotates on its axis at over 1,000 miles per hour at the equator, centrifugal forces cause the planet to bulge outward around its middle, while flattening slightly at the poles. This oblate spheroid shape means that someone standing at sea level at the North Pole is actually significantly closer to the center of Earth's total mass than someone standing at sea level on the equator. Because gravitational attraction scales with the inverse square of the distance between two masses, a person standing at the poles experiences a slightly stronger gravitational pull than they would at the equator. If you weigh yourself at the North Pole, you will weigh roughly 0.5% more than you would at the Amazon basin, even though your actual body mass remains completely identical. However, planetary shape is only one piece of a much larger geological puzzle. The Earth's crust and underlying mantle are a non-uniform mosaic of tectonic plates, continental masses, deep ocean trenches, dense metallic deposits, and magma chambers. Variations in the density of these underground structures create localized gravitational anomalies across the entire globe. Where the Earth's crust is thick, dense, or packed with heavy elements like iron, localized gravity is measurably stronger. Where the crust is thin, porous, or composed of lighter silicate rock, gravity is surprisingly weaker. One of the most famous and extreme examples of this phenomenon occurs in the Hudson Bay region of Canada. During the 20th century, global gravitational surveys revealed that the entire region surrounding Hudson Bay possesses a significantly lower gravitational field than the rest of the planet. For decades, geophysicists debated the primary cause of this missing gravity. Extensive satellite mapping by missions like the Gravity Recovery and Climate Experiment, known as GRACE, eventually unraveled the dual mechanisms behind this massive anomaly. The first major driver dates back to the last ice age, when the massive Laurentide ice sheet buried much of North America beneath a layer of ice over 2 miles thick. The sheer, unfathomable weight of this continental glacier pushed down on the Earth's lithosphere, pressing it deep into the viscous mantle below, much like a finger pressing into a soft memory foam mattress. Roughly 10,000 years ago, the ice sheet melted, removing that immense downward weight. However, the semi-fluid rock of the Earth's mantle flows at an agonizingly slow pace. The surface of the Earth around Hudson Bay is still rebounding upward at a rate of a few millimeters per year, a process known as post-glacial rebound. Because the mantle material has not fully flowed back into the depression under the bay, there is less total mass concentrated beneath the region, creating a persistent drop in gravitational pull. The second driver in Hudson Bay operates even deeper beneath the surface, where ancient mantle convection currents are actively dragging sections of the Earth's crust downward. Together, these two processes create a large regional deficit in Earth's gravitational field, proving that gravity is not a static constant, but a living record of our planet's deep geological history and changing climate. These subtle gravitational variations do far more than just shift sensitivity readouts on scientific instruments. They actively shape the fluid dynamics of our oceans. Water, being a liquid, naturally moves to align itself with localized gravitational variations. In areas where gravity is slightly stronger due to undersea mountains or dense tectonic structures, water is pulled inward, forming subtle humps on the ocean surface that can rise several meters higher than surrounding areas. Conversely, above deep oceanic trenches where mass is lacking, the sea surface sags into broad depressions. The surface of the ocean is not a flat plane, but a dynamic, undulating liquid topology sculpted by the varying density of the seafloor below. Beyond geology and oceanography, gravity's most profound local impact has been its role as the absolute, non-negotiable architect of biological evolution. Every organism that has ever crawled, walked, swum, or flown across this world was designed in direct response to the inescapable downward force of 1g. The size, shape, internal pressure, and structural integrity of all living matter are defined by a perpetual engineering compromise between biological tissues and gravitational acceleration. Consider the physical limits placed upon land animals. As an organism scales up in size, its mass increases cubically according to its volume, while the strength of its bones and muscles increases only quadratically according to their cross-sectional area. This scaling law, known as the square-cube law, dictates that if you take a creature and double its height, length, and width, its weight becomes 8 times greater, but its supporting bones become only 4 times stronger. A tiny ant can easily fall from a tall building and land completely unharmed because its mass is so negligible that air resistance counteracts gravity long before it hits the ground. A human falling from the same height will suffer severe injuries, while an elephant falling from a modest height will shatter its skeletal frame. This mathematical constraint sets strict boundaries for the largest terrestrial animals in Earth's history, such as the titanosaurian sauropods. These gigantic, long-necked dinosaurs, reaching lengths over 100 feet and weighing upwards of 70 metric tons, were biological masterpieces designed to resist gravitational collapse. Their legs evolved into thick, columnar pillars placed directly beneath their massive bodies, acting like load-bearing concrete columns. Their bones were not solid rock, but contained intricate honeycomb structures and air sacs that reduced weight while maintaining maximum structural strength. To support necks stretching 40 feet into the air, they utilized a system of powerful elastic tendons running along their vertebrae, functioning like the cables of a suspension bridge. If a land animal grows too massive, the energy required simply to stand up and pump blood against gravity exceeds the biochemical capacity of its metabolic system. The only reason the blue whale, the largest animal ever known to exist, can reach masses exceeding 180 metric tons is because it lives in an aquatic environment. Water provides buoyant lift, an upward force that counteracts the pull of gravity and distributes the whale's massive weight evenly across its body. When a large whale strands on a beach, it does not die from a lack of oxygen. It suffocates because its own crushing weight collapses its lungs and soft tissues in the absence of water's buoyant support. Gravity has also forced terrestrial life to develop extraordinary internal circulatory adaptations. Consider the giraffe, whose head sits nearly 20 feet above the ground. To push oxygen-rich blood all the way up its long neck against the downward pull of gravity, a giraffe's heart must generate a blood pressure nearly double that of a human, reaching systolic pressures over 280 millimeters of mercury. To prevent this extreme pressure from rupturing the blood vessels in its brain when the giraffe lowers its head to drink, the animal possesses a specialized network of elastic blood vessels at the base of its skull, called the rete mirabile. This tissue acts as a pressure equalizing reservoir, absorbing the rush of blood when the head drops and releasing it smoothly when the head lifts. Furthermore, the skin on a giraffe's lower legs is exceptionally tight and inelastic, acting like natural compression socks that prevent high gravitational pressure from forcing fluid out of the blood vessels and causing severe tissue swelling in its lower extremities. When humans venture away from this evolutionary anchor into the microgravity environment of space, the biological consequences highlight just how deeply our bodies depend on gravity to function normally. Aboard the International Space Station, astronauts exist in a continuous state of freefall. Because their bodies no longer need to work against the constant downward pull of 1g, human physiology begins to adapt to the lack of gravitational demand in ways that are deeply destructive over time. Without gravity pulling fluids toward the feet, fluids shift upward toward the chest and head. Astronauts experience swollen faces, nasal congestion, and a significant increase in intracranial pressure. This condition, known as spaceflight-associated neuroocular syndrome, flattens the back of the eyeball and swells the optic nerve, causing permanent vision impairment in many long-duration space travelers. Simultaneously, the human body realizes it no longer needs a heavy, mineral-dense skeleton to support its weight. Osteoclasts, the cells responsible for breaking down bone tissue, begin to outpace osteoblasts, the cells that build bone. Astronauts lose roughly 1 to 1.5% of their total bone mineral density in the hip and lower spine for every single month spent in microgravity, dumping excess calcium directly into their bloodstream and significantly increasing the risk of painful kidney stones. Muscle tissue suffers a similar fate. Without the constant microscopic contractions required to hold posture against gravity, leg and back muscles rapidly atrophy. Even the human heart, no longer needing to pump blood uphill against gravity, shrinks in mass and changes shape, becoming more spherical. To combat this physical decline, astronauts must spend over 2 hours every day performing intense cardiovascular and resistance exercises using specialized vacuum cylinder weight machines and strap-down treadmills. They are essentially tricking their bodies into believing they are still wrestling with the constant physical burden of Earth's gravity. From the shifting, uneven density of the deep mantle beneath Hudson Bay to the intricate vascular systems of giant organisms and the physical decay of humans floating in orbit, Earth's gravity is far more than an abstract force calculated in a laboratory. It is an active, unequal, and relentless sculptor of both the living tissue and the solid rock of our planet. Outside the immediate physical embrace of our planet's surface, gravity transitions from a local structural architect into the absolute conductor of celestial motion. Everything in our solar system, from the smallest pebble in the main asteroid belt to the colossal gas giant Jupiter, moves in obedience to orbital mechanics, a subtle geometric dance orchestrated entirely by gravity. To understand this dance, we must first abandon the common misconception that space is a place where gravity simply ceases to exist. When we watch videos of astronauts floating inside the International Space Station, it appears as though they have escaped Earth's gravitational pull. In reality, the space station orbits at an altitude of approximately 400 kilometers above the surface. At that distance, the strength of Earth's gravitational field is still roughly 90% as strong as it is on the ground. The astronauts float not because there is no gravity, but because they, along with the space station itself, are in a state of perpetual freefall toward the Earth. They do not crash into the ground because the station possesses a forward horizontal velocity of nearly 27,600 kilometers per hour. As gravity pulls the station downward, its forward momentum carries it so far sideways that the Earth curves away beneath it at the exact same rate. The station is constantly falling around the planet, tracing a stable, closed trajectory known as an orbit. Every satellite, moon and planet operates on this identical principle. An orbit is simply the art of falling without ever hitting the ground. In the early 17th century, before Newton formulated his law of universal gravitation, the German astronomer Johannes Kepler meticulously analyzed decades of observational data collected by Tycho Brahe. Kepler discovered three fundamental laws that describe orbital motion with astonishing precision. First, planets do not move in perfect circles. They trace ellipses with the Sun located at one of the two foci. Second, a line joining a planet and the Sun sweeps out equal areas during equal intervals of time, meaning a planet moves faster when it is closer to the Sun at perihelion and slower when it is farther away at aphelion. Third, the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. Decades later, Isaac Newton demonstrated that Kepler's empirical laws were the direct mathematical consequence of an inverse square gravitational force. Newton expanded our understanding by showing that orbits are not limited to closed ellipses. Depending on an object's velocity, a trajectory through a gravitational field can take the shape of any conic section, a circle or ellipse for bound orbits, or a parabola or hyperbola for unbound escape trajectories. If an object reaches a critical speed, known as escape velocity, approximately 11.2 km per second at Earth's surface, its kinetic energy exceeds its gravitational potential energy, allowing it to break free from the planet's gravitational well and travel into interplanetary space forever. While orbital mechanics keep worlds moving along predictable paths, gravity also exerts differential forces across the physical bodies of planets and moons, creating the powerful phenomenon known as tidal forces. Tidal forces arise because gravity drops off with distance. The side of a celestial body that faces a nearby gravitational source is pulled more strongly than its center, while its far side is pulled less strongly than its center. This difference in gravitational pull stretches the body along the line connecting the two objects. On Earth, this differential force manifests most visibly as ocean tides. The Moon's gravitational pull tugs on Earth's oceans, creating a bulge of water on the side facing the Moon. Simultaneously, because the Moon pulls the solid Earth away from the water on the opposite side, a second tidal bulge forms on the far side of the planet. As the Earth rotates through these two bulges every day, coastal areas experience high tides roughly every 12 hours. The Sun also creates ocean tides, though its immense distance renders its tidal effect roughly half as powerful as the Moon's. When the Sun, Earth, and Moon align during full and new moons, their tidal forces combine to produce unusually extreme spring tides. Conversely, when the Sun and Moon are at right angles relative to Earth, their tidal forces partially cancel out, resulting in milder neap tides. Tidal forces do not merely move water, they deform solid rock. The Moon flexes the solid crust of the Earth by several centimeters twice every day. Over cosmic timescales, this gravitational friction transfers rotational energy from the Earth to the Moon. The Earth's rotation is slowing down by roughly 2 milliseconds per century, while the Moon is being pushed into a slightly higher orbit, receding from the Earth at a rate of approximately 3.8 centimeters per year. In the distant past, when the Moon was much closer, Earth's days were significantly shorter, and coastal ocean tides were towering walls of water hundreds of feet high. When tidal forces become extreme, they can transform from gentle modifiers into destructive engines of cosmic destruction. Every celestial body held together by its own gravity has a critical distance threshold known as the Roche limit. If a smaller moon or asteroid approaches a massive planet closer than this threshold, the differential gravitational force between its near and far sides becomes stronger than the internal gravitational forces holding the smaller body together. The planet's gravity literally tears the Moon apart, ripping it into millions of fragments. The spectacular, shimmering rings of Saturn are a vivid manifestation of the Roche limit in action. Astronomers hypothesize that Saturn's rings are the icy remains of an ancient moon or comet that ventured inside Saturn's Roche limit billions of years ago and was torn into countless icy particles. These ring particles remain trapped in orbit around Saturn's equator today, unable to ever clump together to reform a solid moon because Saturn's relentless tidal forces continually disrupt any attempt at gravitational reaccumulation. Conversely, tidal forces can serve as an intense source of internal heat. Jupiter's moon Io is the most volcanically active world in the entire solar system, covered in hundreds of active volcanic vents spewing plumes of sulfur dozens of miles into space. Io orbits close to Jupiter while being continuously tugged by the gravitational resonances of neighbouring moons Europa and Ganymede. This gravitational tug-of-war forces Io into an eccentric orbit, where Jupiter's tremendous tidal forces continuously flex and squeeze the moon's solid interior. This process, known as tidal heating, generates immense internal friction, melting Io's mantle into a churning subsurface ocean of magma that erupts relentlessly across its surface. While gravity can tear worlds apart or melt them from within, humans have learned to turn this relentless force into a cosmic tool for exploration through the technique of gravitational slingshots or gravity assists. When space agencies send robotic probes to the outer reaches of the solar system, chemical rockets alone are often insufficient to provide the massive velocity required to reach distant targets like Jupiter, Saturn, or interstellar space within a human lifetime. To overcome this propulsion limit, mission planners calculate trajectories that send spacecraft on precise flybys of intermediate planets. As a spacecraft approaches a planet like Venus, Earth, or Jupiter, it drops into the planet's gravitational well, accelerating as it falls. If the spacecraft approaches from behind the planet relative to the planet's orbital motion around the Sun, it steals a microscopic fraction of the planet's orbital momentum. Because the planet is enormously more massive than the tiny probe, the planet slows down by an imperceptible, infinitesimal amount, while the spacecraft gains a massive boost in velocity and a sharp change in direction relative to the Sun. The Voyager 1 and Voyager 2 spacecraft utilized a rare alignment of Jupiter, Saturn, Uranus, and Neptune in the late 1970s to perform a sequence of gravitational slingshots, jumping from world to world and gaining enough speed to permanently escape the gravitational pull of the Sun and enter interstellar space. From the precise elliptical tracks of distant planets to the daily sloshing of coastal seas, from the planetary debris fields of Saturn's rings to the hypervolcanism of Io and the slingshot trajectories of our outward-bound probes, gravity acts as both a delicate orbital thread and a destructive hammer. It governs every movement in our solar system through a balance of speed, distance, and mass, setting the stage for the far more violent gravitational extremes found deeper in the galactic void. Throughout the life cycle of a massive star, gravity exists in a perpetual tug-of-war against the outward pressure of thermal radiation. For millions of years, nuclear fusion deep within the stellar core fuses hydrogen into helium, then helium into carbon, oxygen, neon, silicon, and eventually iron. This nuclear furnace generates tremendous thermal pressure, pushing outward and perfectly balancing the relentless inward crush of the star's colossal gravitational mass. This state of hydrostatic equilibrium keeps the star stable. However, iron represents a hard physical limit in nuclear physics. Fusing iron atoms does not release energy, it consumes it. When a star possessing more than 8 times the mass of our Sun develops an iron core, its internal fuel engine abruptly shuts down. Within a fraction of a second, radiation pressure drops to 0. Without the outward pressure to counteract it, gravity instantly wins the cosmic tug-of-war. The star's core undergoes a catastrophic gravitational collapse, rushing inward at a significant fraction of the speed of light. The sheer magnitude of this collapse compresses a stellar core larger than the Earth into a sphere roughly 20 kilometers in diameter, about the size of a city, in less than a single second. The gravitational collapse is so violent that it shatters the fundamental atomic structure of matter itself. Under ordinary conditions, atoms consist of vast empty spaces with tiny electrons orbiting a dense atomic nucleus. But the intense inward pressure generated by the collapsing core forces negatively charged electrons to merge directly with positively charged protons, producing a flood of neutrinos and transforming the core into a solid mass of tightly packed neutrons. This process, known as neutronization, halts the collapse only when the neutrons are jammed so tightly together that quantum mechanics intervenes. A phenomenon called neutron degeneracy pressure, the absolute physical refusal of identical neutrons to occupy the same quantum state, finally halts gravity's crushing weight. The result of this violent stellar death is a supernova explosion that scatters the star's outer layers into space, leaving behind an exotic remnant object, a neutron star. A neutron star represents one of the most extreme environments in the universe, a place where gravity has pushed matter to the absolute edge of physical existence, short of becoming a black hole. Although a neutron star measures only about 12 to 20 kilometers across, it packs the equivalent mass of roughly 1.4 to 2 times that of our Sun. To put this extraordinary density into perspective, a single sugar cube-sized piece of neutron star material would weigh approximately 6 billion tons on Earth, roughly equivalent to the weight of every human being, building and vehicle on our planet combined. If you were to drop an object onto the surface of a neutron star from a height of just 1 meter, it would accelerate under the neutron star's immense gravity to a speed of millions of kilometers per hour in less than a microsecond, smashing into the surface with enough energy to unleash a massive explosion. The gravitational pull at the surface of a neutron star is roughly 200 billion times stronger than the gravity we experience on Earth. This immense gravity smooths out the surface of the neutron star to a degree that is difficult to comprehend. Any mountain or surface irregularity on a neutron star can rise no higher than a few millimeters or fractions of a millimeter before gravity crushes it flat. The surface crust of a neutron star, composed of crystalline iron polymer chains embedded in a sea of electrons, is estimated to be 10 billion times stronger than steel. Because the progenitor star's original angular momentum and magnetic flux are compressed into a tiny volume, neutron stars rotate at bewildering speeds and possess colossal magnetic fields. Some young neutron stars, known as pulsars, rotate hundreds of times per second, emitting beams of intense electromagnetic radiation from their magnetic poles like cosmic lighthouses. As these beams sweep past Earth's line of sight, radio telescopes detect precise, repeating pulses of energy. Other neutron stars, known as magnetars, possess magnetic fields up to 1 quadrillion times stronger than Earth's, so intense that they can strip electrons from nearby atoms and warp the quantum vacuum itself. However, neutron degeneracy pressure has a strict, absolute ceiling known as the Tolman-Oppenheimer-Volkoff limit. Named after the physicists who first calculated it, this limit dictates that neutron degeneracy pressure can only withstand a maximum gravitational mass of approximately 2 to 3 solar masses. If the collapsing stellar core exceeds this critical mass threshold, or if a neutron star accretes enough additional material from a binary companion star, neutron degeneracy pressure completely fails. When the Tolman-Oppenheimer-Volkoff limit is breached, no known force or physical barrier in the universe can halt the relentless advance of gravity. The matter is crushed past the boundaries of atomic existence, past the limits of subatomic particles, and past the structural threshold of space and time itself. Great achieves an absolute victory over matter, triggering an unending inward collapse that leaves the realm of normal physics behind and creates the ultimate cosmic trap, a black hole. When a collapsing stellar core exceeds the Tolman-Oppenheimer-Volkoff limit, gravity achieves an absolute and terrifying victory over matter. With no physical pressure remaining to halt the inward collapse, the core collapses past its own critical gravitational radius, known as the Schwarzschild radius. At this threshold, the curvature of space-time becomes so severe that space effectively closes in upon itself. The result is a stellar mass black hole, an object where gravity has warped the fabric of the universe so violently that nothing, not even light, the fastest entity in existence, can escape its grasp. The outer boundary of a black hole is not a solid, tangible surface made of matter. It is a mathematical and physical boundary called the event horizon. The event horizon marks the point of no return. Beyond this invisible sphere, the escape velocity required to break free from the black hole's gravitational pull exceeds 300,000 kilometers per second, the speed of light in a vacuum. Because light itself cannot escape, Any event occurring inside the event horizon can never transmit information or light to the outside universe. The interior of a black hole is completely severed from our observable reality. To understand how warped space becomes near an event horizon, consider the trajectory of light rays. Outside a black hole, light can travel in any direction. As light approaches the event horizon, the extreme space-time curvature bends its path so severely that only light rays directed almost straight outward can escape into deep space. At a specific radius outside the event horizon, a region called the photon sphere, the curvature of space is so precise that light rays are forced into circular orbits around the black hole. If an observer could stand safely within the photon sphere, light reflecting off the back of their head would orbit the black hole and enter their own eyes, allowing them to see the back of their own head floating in space ahead of them. Inside the event horizon, the very geometry of space and time undergoes a profound transformation. In our normal universe, we can move freely back and forth in 3 spatial dimensions, but we are dragged relentlessly forward in time toward the future. Inside a black hole, the roles of space and time are inverted. Space becomes unidirectional, moving inward toward the center of the black hole becomes as physically inevitable as moving forward in time is for us in our daily lives. Every path through space, regardless of propulsion or direction, leads directly toward the center. Seeking an exit out of an event horizon is as impossible as traveling backward into yesterday. At the absolute center of a non-rotating black hole lies the singularity. In classical general relativity, the singularity is a point of zero volume and infinite density, where an enormous amount of mass is crushed into an infinitesimally small space. At this point, the curvature of spacetime becomes infinite, and the known laws of physics cease to function. Equations yield meaningless mathematical infinities. The concept of space and time as continuous, smooth structures breaks down entirely. Whether a true physical singularity exists or whether quantum effects intervene at extremely tiny scales remains one of the greatest unresolved questions in modern physics. The gravitational field surrounding a black hole also produces the most severe gravitational time dilation observable in the cosmos. According to Einstein's equations, as an object approaches an immense gravitational mass, time slows down relative to an observer located far away in flat space-time. Near the event horizon of a black hole, this effect reaches its absolute limit. Imagine a daring astronaut wearing a synchronized clock hovering near the event horizon of a supermassive black hole while a colleague observes from a safe distance far away in deep space. To the astronaut hovering near the horizon, their clock ticks normally, 1 second at a time. Their heart beats at a regular rate, and their thoughts move at ordinary speeds. Local time flows normally for the astronaut within their own reference frame. However, to the distant observer watching through a powerful telescope, a staggering illusion unfolds. As the astronaut drops closer to the event horizon, the signals emitted from their suit take longer and longer to escape the deep gravitational well. The distant observer sees the astronaut's clock slow down drastically. Seconds stretch into minutes, minutes into hours, and hours into years. The light coming from the astronaut becomes increasingly redshifted, shifting toward longer radio wavelengths and fading in brightness. As the astronaut reaches the exact radius of the event horizon, time for them appears to freeze completely from the perspective of the distant observer. The astronaut seems frozen in time at the boundary, fading away as the light shifts into extreme infrared and radio frequencies. The distant observer will never actually see the astronaut cross the event horizon. They will only see them approach it infinitely slowly over an infinite expanse of time. Yet, from the personal perspective of the falling astronaut, their experience is terrifyingly different. They cross the event horizon in a finite amount of local time, noticing no sudden physical barrier at the boundary itself. However, as they descend, they experience extreme tidal forces caused by the steep gradient of gravity over short distances. Because the gravitational pull on their feet is drastically stronger than the pull on their head, their body is stretched vertically and compressed horizontally in a process known as spaghettification. For a stellar mass black hole, these tidal forces are so intense that they tear the astronaut apart into individual atoms long before they even reach the event horizon. For a supermassive black hole containing millions or billions of solar masses, the event horizon is vast, and the tidal forces at the boundary are gentle enough that an astronaut could cross the horizon unharmed, only to meet their inevitable destruction as they rush toward the singularity at the center. Through the event horizon, the singularity, and extreme gravitational time dilation, black holes demonstrate what happens when gravity operates completely unchecked by matter or radiation. They are not merely massive vacuum cleaners sweeping through space, but places where the fabric of spacetime reaches its absolute geometric limits, challenging everything we understand about the true nature of reality. For over a century after Albert Einstein published his theory of general relativity, one of its most astonishing theoretical predictions remained completely unverified. Einstein's equations showed that if space and time form a dynamic, flexible fabric, then massive accelerating objects should not merely warp that fabric statically, they should create moving ripples in the geometry of space itself. These ripples are known as gravitational waves. To understand what a gravitational wave actually is, we must abandon the idea of waves moving through space, such as sound waves traveling through air or water waves moving across the surface of a pond. A gravitational wave is not a wave traveling through space. It is a wave of space itself. As a gravitational wave passes through a region of the universe, it stretches space in one transverse direction while simultaneously compressing it in the perpendicular direction. If a gravitational wave were passing directly through your room right now, the space between your left and right shoulders would momentarily expand, while the space between your head and feet would contract, followed immediately by the opposite distortion as the wave oscillated past. However, space-time is an exceptionally rigid fabric. It requires catastrophic amounts of energy to produce ripples large enough to measure. Everyday accelerations, such as a car driving down a highway or a jet accelerating through the sky, generate gravitational waves that are infinitely tiny, utterly lost in quantum noise. Even the violent movements of planets orbiting the Sun produce waves so microscopic that they are fundamentally undetectable by any technology humans could ever build. To generate gravitational waves capable of being detected across cosmic distances, the universe must stage events of extremely violent energy involving massive, ultra-dense objects. The ideal cosmic engines for producing measurable gravitational waves are binary systems composed of two neutron stars or two black holes orbiting each other at close range. As these colossal masses spiral around their common center of mass, they continuously radiate energy outward into the universe in the form of gravitational waves. As energy radiates away, the two massive bodies draw closer together, orbiting faster and faster in a runaway process called an orbital in spiral. During the final split seconds before they collide and merge, the two objects orbit each other hundreds of times per second at a significant fraction of the speed of light. This frantic motion churns the surrounding space-time continuum, broadcasting high-frequency gravitational waves radiating outward across the cosmos at the exact speed of light. Einstein calculated the mathematical existence of these waves in 1916, but he believed humanity would never possess instruments sensitive enough to detect them. The distortion caused by a passing gravitational wave, by the time it travels hundreds of millions of light-years to reach Earth, is incomprehensibly tiny. A typical gravitational wave stretches and compresses a kilometre-long stretch of space by a fraction of a proton's width, roughly 1 part in 10 to the 21st power. Detecting such a microscopic change in distance seemed physically impossible. For decades, gravitational waves remained a purely theoretical concept. The first indirect evidence of their existence emerged in 1974, when astronomers Russell Hulse and Joseph Taylor discovered the first binary pulsar, known as PSR B 1913+16. This system consists of a neutron star and a pulsar orbiting each other in a tight, rapid orbit. By tracking the ultra-precise timing of the pulsar's radio pulses over several years, Hulse and Taylor discovered that the two stars were drawing closer together, and their orbital period was decaying at the exact rate predicted by general relativity if the system were losing energy through gravitational wave emissions. This landmark discovery earned them the Nobel Prize in Physics in 1993, but direct detection of the waves themselves remained elusive. The dream of directly capturing a gravitational wave required a radical leap in experimental physics. Decades of engineering culminated in the construction of the Laser Interferometer Gravitational Wave Observatory, known as LIGO. Funded by the National Science Foundation in the United States, LIGO consists of two identical giant observatories separated by 3,000 kilometers, one located in Hanford, Washington, and the other in Livingston, Louisiana. Each LIGO facility is a massive L-shaped instrument featuring two ultra-high vacuum arms, each extending precisely 4 kilometers long. At the intersection of the arms, a high-power laser beam is split into two perpendicular beams traveling down the vacuum tubes. At the end of each 4-kilometer arm, the laser light bounces off highly polished mirrors suspended on multi-stage pendulum systems, returning to merge at the central detector. Under normal conditions, the light paths are tuned so that the returning light waves interfere destructively, cancelling each other out so that no light reaches the detector. However, when a gravitational wave passes through the observatory, it stretches one 4-kilometer arm while compressing the other by an imperceptible margin. This microscopic variance changes the distance the laser beams travel, destroying the perfect destructive interference. As a result, a subtle flicker of light reaches the photodetector, encoding the precise frequency and amplitude of the passing space-time ripple. The engineering required to achieve this sensitivity is staggering. LIGO must measure a change in the length of its 4-kilometer arms, smaller than 1/10,000th the diameter of a single proton. To isolate the mirrors from external vibrations such as distant ocean waves, highway traffic, earthquake tremors, or thermal fluctuations, the mirrors are suspended by ultra-pure fused silica fibers inside one of the largest ultra-high vacuum chambers on Earth, stabilized by active seismic isolation systems. On September 14, 2015, at 10:51 Universal Time, LIGO made history. A burst of gravitational waves passed through Earth, striking the detector in Livingston, Louisiana, and then, 7 milliseconds later, arriving at the detector in Hanford, Washington. The signal matched the theoretical predictions of general relativity with absolute mathematical precision. The signal, designated GW150914, was created by the violent collision and merger of two stellar mass black holes, one roughly 29 times the mass of the Sun and the other 36 times the mass of the Sun, located 1.3 billion light-years away. In the final fraction of a second before the two black holes merged into a single spinning black hole, they radiated an amount of energy equivalent to 3 full solar masses directly into gravitational waves. For that brief moment, the gravitational energy output of that single merger was dozens of times greater than the combined light output of every star in the entire observable universe. The direct detection of gravitational waves was announced to the world in February 2016, validating Einstein's final major prediction exactly 1 century after he proposed it. Rainer Weiss, Kip Thorne, and Barry Barish were awarded the Nobel Prize in Physics in 2017 for their decisive contributions to the LIGO project and the observation of gravitational waves. The true significance of LIGO's breakthrough extends far beyond simply verifying Einstein's theory. For thousands of years, human astronomy was restricted to observing the universe through light, first through optical telescopes, and later through radio waves, X-rays, gamma rays, and infrared sensors. But electromagnetic radiation can be blocked, scattered, or absorbed by interstellar gas and dust. Black holes, by their very nature, emit no light whatsoever. Gravitational waves are fundamentally different. They do not travel through space like light. They are movements of space itself. They pass completely unhindered through solid matter, cosmic dust clouds, and dense plasma. Detecting gravitational waves gave humanity an entirely new sense. If optical astronomy is like looking at the universe, gravitational wave astronomy is like listening to it. This revolution reached its peak on August 17, 2017, when LIGO and its European partner observatory, Virgo, detected signal GW170817. Unlike previous detections, this signal was generated by the collision of two neutron stars, located 130 million light-years away in the galaxy NGC 4993. Because neutron stars are made of dense physical matter rather than pure space-time curvature, their collision unleashed a massive explosion known as a kilonova, emitting electromagnetic radiation across the spectrum. Just 1.7 seconds after the gravitational wave signal ended, space-based gamma-ray telescopes detected a bright burst of gamma rays coming from the exact same region of the sky. Over the following days and weeks, optical, infrared, radio, and X-ray telescopes around the world focused on the location, capturing the visual aftermath of the merger. This historic event marked the birth of multi-messenger astronomy, the ability to observe the exact same cosmic event simultaneously through both gravitational ripples and electromagnetic light. The multi-messenger observation of GW 170817 solved long-standing cosmic mysteries. It proved that short gamma-ray bursts are produced by neutron star mergers, verified that gravitational waves travel at the exact speed of light to within 1 part in a quadrillion, and confirmed that neutron star collisions are the primary cosmic factories where heavy elements like gold, platinum, and uranium are forged in the universe. Through the discovery of gravitational waves and the emergence of multi-messenger astronomy, gravity transitioned from an elusive force we struggle to understand into a revolutionary sensory system for mapping the most violent, silent, and mysterious phenomena scattered across the fabric of space and time. Despite the profound triumphs of Einstein's General Relativity in explaining planetary orbits, the bending of starlight, and the existence of gravitational waves, our understanding of gravity faces a massive cosmic contradiction when we look beyond individual solar systems and zoom out to the vast scales of entire galaxies. When astronomers measure the total amount of visible mass contained within spiral galaxies and apply the accepted laws of gravity, the math fails completely. The universe appears to be dominated by an invisible ghost whose gravitational pull holds everything together, yet remains entirely undetected by any light-based instrument. This profound crisis began to surface in the early 20th century. In 1933, the Swiss-American astronomer Fritz Zwicky was studying the Coma Cluster, a massive collection of thousands of galaxies bound together by gravity. Zwicky attempted to calculate the total mass of the cluster by measuring the light emitted by all its constituent galaxies. He then measured the individual velocities of these galaxies as they orbited around the center of the cluster. According to Newtonian gravitational mechanics and general relativity, the total gravitational force holding a cluster together depends entirely on its total mass. If galaxies move too quickly, their kinetic energy will overcome the gravitational pull of the cluster, causing the individual galaxies to fly apart into deep space, like unanchored objects flying off a rapidly spinning carousel. When Zwicky calculated the velocities of the galaxies within the Coma Cluster, he received a profound shock. The galaxies were moving so fast that the gravitational pull generated by all the visible stars, gas, and dust in the cluster was nowhere near strong enough to keep them bound together. By all known laws of physics, the Coma Cluster should have dissolved billions of years ago, scattering its galaxies across the cosmos. To explain why the cluster remained intact, Zwicky proposed that there must exist a vast amount of unseen, non-luminous matter providing the extra gravitational pull required to anchor the cluster. He called this mysterious substance dunkel Materie, or dark matter. For decades, many scientists dismissed Zwicky's findings as an anomaly or a measurement error. However, in the 1970s, the American astronomer Vera Rubin, working alongside Kent Ford, provided definitive, undeniable proof that this gravitational paradox was not an isolated fluke, but a fundamental feature of nearly every galaxy in the universe. Vera Rubin turned her attention to spiral galaxies, including our neighboring Andromeda galaxy and our own Milky Way. Spiral galaxies consist of a dense central bulge of stars surrounded by a thin, rotating disk of gas, dust, and stars. Under classical mechanics, the speed at which an object orbits around a central mass depends on its distance from that mass. In our own solar system, Keplerian dynamics dictate that planets close to the massive Sun move extremely fast. Mercury orbits at 47 kilometers per second, while planets located far out on the icy fringes move much slower. Neptune orbits at just 5 kilometers per second. Astronomers assumed that spiral galaxies would follow this identical orbital pattern, known as a Keplerian rotation curve. Because the vast majority of a galaxy's visible mass, billions of bright stars and vast clouds of dense gas, is concentrated in its bright central bulge, stars orbiting near the galactic center were expected to move rapidly. Meanwhile, stars located far out on the sparse, dark edges of the galactic disk were expected to move progressively slower as their distance from the central mass increased. To test this assumption, Rubin and Ford used precise spectrographs to measure the Doppler shifts of light coming from hydrogen gas clouds situated at varying distances from the centers of spiral galaxies. They plotted these orbital speeds against distance to build galactic rotation curves. The results completely shattered existing expectations. The rotation curves did not drop off at all. Instead of slowing down near the outer edges of the galaxies, the orbital velocities of outer stars remained flat. Stars situated at the extreme outer edges of galactic disks, where visible matter drops to almost zero, were moving through space at virtually the exact same high speeds as stars orbiting close to the dense central bulge. Mathematically, this flat rotation curve presented an impossible dilemma. The outer stars were moving so fast that the gravitational pull generated by all the visible matter inside the galaxy was utterly insufficient to hold them in orbit. Based on the amount of light these galaxies emit, their outer stars should be flung out into interstellar space, causing the spiral arms to tear apart and disintegrate. Yet these galaxies remain stable, beautifully structured, and tightly bound. To prevent these outer stars from flying off into space, galaxies must contain vastly more mass than we can see. Astronomers calculated that to produce the flat rotation curves measured by Rubin, each spiral galaxy must be embedded inside an enormous, spherical cloud of invisible matter known as a dark matter halo. This halo must extend far beyond the visible borders of the galaxy's stars and gas, containing roughly 5 times more mass than all the visible matter combined. Subsequent observations across multiple branches of astrophysics have confirmed this disturbing reality. When astronomers map the distribution of mass in the cosmos using gravitational lensing, measuring how the gravity of massive objects bends the light from distant background galaxies, they consistently find massive concentrations of invisible gravity where no visible matter exists. Furthermore, measurements of the cosmic microwave background, the faint heat echo left behind by the Big Bang, reveal that dark matter was essential for the early structure of the universe. In the infant cosmos, dark matter clumped together under its own gravity first, forming invisible gravitational wells. Ordinary matter, made of atoms, then fell into these dark matter wells, eventually cooling and condensing to form the very first stars, galaxies, and planetary systems. Without the invisible scaffolding of dark matter, the universe as we know it could never have formed. Yet, despite its overwhelming gravitational footprint across the cosmos, dark matter remains an absolute enigma. It does not absorb, reflect, refract, or emit any form of electromagnetic radiation. It produces no light, no radio waves, no X-rays, and no heat. It passes completely unhindered through ordinary matter, like phantom ghost matter moving through solid walls. Right now, trillions of dark matter particles may be passing through your body every single second without interacting with a single atom of your skin or bones. Physicists hypothesize that dark matter is composed of an undiscovered type of subatomic particle that interacts almost exclusively through gravity and possibly the weak nuclear force. Theoretical candidates include weakly interacting massive particles, known as WIMPs, ultralight particles called axions, or sterile neutrinos. For decades, researchers have built ultra-sensitive detectors deep underground in abandoned mines, shielded under miles of rock to isolate them from cosmic rays, searching for the faint recoil of an ordinary atomic nucleus colliding with a dark matter particle. High-energy particle colliders have also attempted to produce dark matter particles artificially. To date, every single direct detection experiment has returned 0 confirmed results. Dark matter remains a ghost, a fundamental entity known exclusively through its gravitational effects, yet completely invisible to our standard model of particle physics. We are forced to confront a staggering scientific reality. The ordinary matter that makes up every star, planet, gas cloud, tree, ocean, and human being in existence accounts for only about 5% of the total mass-energy content of the cosmos. The rest is hidden in the dark, stretching our understanding of gravity to its absolute limits. If dark matter represents an invisible gravitational tether holding galaxies together, the discovery made at the end of the 20th century revealed an even more terrifying counterforce operating across the cosmic expanse. For decades, cosmologists assumed that the ultimate fate of the universe was governed by a simple tug-of-war between the outward expansion initiated by the Big Bang and the inward pull of total universal gravity. Depending on how much total matter existed, the universe would either possess enough gravitational mass to eventually halt its expansion and collapse back into a big crunch, or it would expand forever at a gradually slowing pace. In 1998, two independent teams of astronomers, the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project led by Saul Perlmutter, set out to measure this expected deceleration of the cosmos. They utilized Type 1a supernovae as cosmic standard candles. Type 1a supernovas occur when a dense white dwarf star accretes matter from a binary companion until it reaches a precise mathematical mass limit, triggering a thermonuclear explosion of uniform intrinsic brightness. By comparing how bright these supernovas appeared to how fast their host galaxies were receding from Earth, astronomers could calculate precise distances across deep cosmic time. The observational results shocked the scientific world and earned the researchers the Nobel Prize in Physics in 2011. The universe was not slowing down in its expansion, it was speeding up. Galaxies were accelerating away from each other at an ever-increasing rate. To account for this cosmic acceleration, physicists were forced to introduce a new, mysterious entity that permeates all of space: dark energy. Dark energy is an anti-gravitational agent that acts as a repulsive force across vast intergalactic distances. Unlike matter or radiation, which dilutes as space expands, dark energy possesses a constant energy density inherent to the vacuum of space itself. As the universe expands and creates more volume, the total amount of dark energy increases, driving an ever more violent acceleration. In Einstein's field equations of general relativity, dark energy can be represented mathematically as the cosmological constant, denoted by the Greek letter lambda. Originally introduced by Einstein in 1917 as a theoretical fudge factor to force his equations to model a static, non-expanding universe, he famously discarded it after Edwin Hubble proved the universe was expanding, calling it his greatest blunder. Yet, decades later, modern observational cosmology resurrected lambda to describe the acceleration driven by dark energy. Measurements conducted by space observatories, such as the Planck satellite, have established a precise budget of the universe. Dark energy constitutes approximately 68% of the total mass energy content of the observable cosmos. Dark matter accounts for roughly 27%. Ordinary baryonic matter, the protons, neutrons, and electrons that form every visible star, galaxy, planet, and living creature, makes up less than 5% of reality. 95% of the cosmos is comprised of dark components whose physical nature remains completely unknown. This cosmic balance sets the stage for a grand battle between gravity and dark energy. On localized dense scales, within galaxies, star clusters, and solar systems, gravity remains dominant, keeping stars in orbit and holding atoms together. But on larger scales, across the vast cosmic voids separating galactic superclusters, dark energy easily overpowers gravity's attractive reach. The ultimate fate of our universe depends entirely on the fundamental nature and future behavior of dark energy. Cosmologists have modeled three primary scenarios for how this cosmic struggle might end over trillions of years. The first and most widely accepted scenario is known as the Big Freeze or heat death. Under this outcome, dark energy continues to drive the accelerated expansion of space indefinitely. Over hundreds of billions of years, galaxies located outside our locally bound gravitationally merged supercluster will be pushed beyond our cosmic horizon, traveling away from us faster than the speed of light. The night sky will slowly grow dark, empty, and lonely. Inside isolated galaxies, stars will burn through their remaining nuclear fuel one by one, fading into cold white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through Hawking radiation over unfathomable timescales, leaving behind a cold, dark, uniform sea of subatomic particles stretching across an ever-expanding void where no work can be extracted and no energy transformations can occur. The second, more catastrophic scenario is known as the Big Rip. If dark energy is not a constant vacuum energy, but a dynamic field called phantom energy that grows stronger over time, its repulsive force will eventually overcome every bound structure in existence. In the final moments of the universe, dark energy will first pull entire galaxies apart, then overcome the gravitational pull of individual stars and planetary systems, shattering Earth and the Sun. Minutes before the end, atomic structures will be torn apart as dark energy overcomes the strong and weak nuclear forces. Finally, at the ultimate instant of the Big Rip, the fabric of spacetime itself will be shredded into infinite density. The third, speculative scenario is the Big Bounce. If dark energy is a dynamic, shifting field that eventually weakens or decays over cosmic epochs, the gravity of the total mass in the universe could one day regain the upper hand. The accelerated expansion would halt, reverse, and begin an accelerating contraction, pulling galaxies back together until the entire universe collapses into an ultra-dense, ultra-hot singularity, potentially triggering a brand new Big Bang and repeating the cycle of cosmic existence. Whether the universe ends in a silent freeze, a violent rip, or a cyclic bounce, dark energy demonstrates that gravity is not the sole dictator of cosmic evolution. Gravity may hold the local pieces of the universe together, but dark energy commands the grand canvas upon which space and time unfold, driving the cosmos toward a distant, mysterious horizon. At the macroscopic scale, Einstein's theory of general relativity reigns supreme. It describes the motions of planets, the warping of starlight, the merging of black holes, and the grand expansion of the observable universe with breathtaking geometric perfection. Simultaneously, at the microscopic scale, quantum mechanics stands as an equally flawless triumph of modern science. It dictates the behavior of subatomic particles, the interactions of light and matter, the structure of atoms, and the foundation of modern technology through the strange rules of wave functions, superposition, and quantum uncertainty. Yet, despite both theories being tested and verified to astonishing levels of experimental precision, they are fundamentally, irreconcilably incompatible with one another. When physicists attempt to apply the smooth, deterministic mathematics of general relativity to the wild, probabilistic realm of quantum mechanics, the equations break down entirely, producing nonsensical mathematical infinities and physical impossibilities. This deep structural contradiction is known as the quantum gravity crisis, and it represents the single greatest unresolved problem in all of theoretical physics. To understand why these two theoretical pillars refuse to coexist, we must examine their opposing visions of the fabric of reality. In general relativity, space and time form a continuous, smooth, and predictable four-dimensional manifold. You can zoom in on a region of space-time as far as you wish, and it will remain completely smooth, like a sheet of flawless glass. Gravity is not a traditional physical force carrying discrete quanta of energy. It is merely the continuous geometric curvature of this pristine, malleable fabric. Quantum mechanics, however, asserts that the universe is fundamentally granular, discrete, and inherently uncertain. Energy, charge, momentum, and angular spin do not exist as smooth, continuous flows. They are divided into indivisible packages called quanta. Furthermore, the Heisenberg uncertainty principle dictates that you cannot simultaneously measure the exact position and momentum of a subatomic particle. The more precisely you pin down an object's location in space, the more uncertain and violent its momentum and energy become. When you apply this quantum uncertainty to the fabric of space-time itself at ultra-tiny scales, the smooth, peaceful geometry described by Einstein completely dissolves. At a microscopic scale known as the Planck length, approximately 1.6 times 10 to the negative 35 meters, a scale a trillion times smaller than a single hydrogen atom, the uncertainty principle creates violent, random fluctuations in energy and geometry. At this Planck scale, space and time cease to be smooth and continuous. Instead, space-time boils into a chaotic, turbulent, rapidly shifting foam known as quantum foam. Virtual particles and microscopic black holes spontaneously form and annihilate in fractions of a second. Space twists, tears, and connects through transient wormholes. In this violent quantum realm, the concept of a smooth geodesic path or a predictable space-time curvature becomes completely meaningless. Einstein's differential equations, built on the assumption of a smooth continuum, cannot function inside quantum foam. The crisis deepens when we attempt to integrate gravity into the standard model of particle physics. The standard model successfully unifies three of the four fundamental forces of nature under a single quantum framework known as quantum field theory. The electromagnetic force is mediated by the exchange of massless particles called photons. The strong nuclear force, which binds quarks together inside protons and neutrons, is mediated by particles called gluons. The weak nuclear force, responsible for radioactive decay, is mediated by massive W and Z bosons. Each of these three forces operates via the exchange of force-carrying gauge bosons across quantized fields. It is therefore entirely natural for physicists to hypothesize that gravity must also possess its own force-carrying quantum particle. This theoretical quantum mediator of gravity is named the graviton. In theory, the graviton is a massless, spin-2 elementary particle that travels at the speed of light, carrying the gravitational interaction between masses at the subatomic level. Just as a beam of light can be described both as a continuous wave and as a stream of individual photons, gravitational waves in a quantum universe should theoretically consist of a vast flux of individual gravitons. However, searching for or mathematically incorporating the graviton has proved to be an absolute nightmare for theoretical and experimental physicists alike. Mathematically, when quantum field theorists try to calculate the interactions between two gravitons using standard perturbative techniques, they run into catastrophic mathematical divergences. When calculating quantum interactions for forces like electromagnetism, physicists use a mathematical procedure called renormalization. Virtual particle interactions can produce infinities, but in quantum electrodynamics, these infinities can be systematically absorbed and cancelled out by redefining a finite number of physical constants, such as the charge and mass of the electron. Renormalization yields finite, hyper-accurate predictions that match laboratory experiments to over 10 decimal places. Gravity, however, is fundamentally non-renormalizable. Because gravity couples directly to energy and momentum, and because gravitons themselves carry energy and momentum, gravitons must interact gravitationally with other gravitons. When you attempt to calculate graviton interactions at high energies, every single loop of virtual graviton interactions introduces new, higher-order mathematical infinities that require an infinite number of new parameters to cancel out. A theory that requires an infinite number of arbitrary inputs to yield an answer is mathematically useless. It predicts everything and therefore predicts nothing. From an experimental standpoint, detecting a single graviton is so extraordinarily difficult that many physicists believe it may be physically impossible within our universe. Because gravity is vastly weaker than the other fundamental forces, a septillion times weaker than electromagnetism, the interaction cross-section of an individual graviton with matter is infinitesimally tiny. To build a detector capable of capturing a single graviton with reasonable efficiency, physicists calculate that the detector would need to possess a mass roughly equivalent to that of the planet Jupiter, and it would need to be placed in orbit extremely close to an intense source of gravitons, such as a neutron star. Even then, the detector would be completely blinded by an overwhelming background flux of neutrinos, which would produce fake signals that no known shielding could block. The graviton remains a necessary theoretical ghost, completely isolated from experimental verification. This profound mathematical and experimental impasse leaves modern physics divided into two isolated realms. When we analyze giant cosmic systems where mass is large and quantum effects are negligible, such as orbiting planets or expanding galaxies, we use general relativity and ignore quantum mechanics. When we analyze atomic systems where mass is tiny and quantum effects dominate, such as microchips or chemical reactions, we use quantum mechanics and ignore general relativity. For 99% of scientific applications, this theoretical separation works perfectly. However, there are two extreme places in our universe where enormous masses and subatomic scales overlap completely: the central singularity of a black hole and the initial birth instant of the Big Bang. Inside a black hole, an enormous amount of mass is compressed into a region smaller than the Planck length. At the moment of the Big Bang, the entire observable universe was packed into a region far smaller than a subatomic particle. In these extreme environments, gravity is immensely strong, meaning general relativity is required. Yet the spatial scale is subatomic, meaning quantum mechanics is equally required. Because the two theories contradict each other, physics currently cannot describe what actually happens inside a black hole, or what occurred at the exact moment the universe was born. When we ask our current equations what happens at the central singularity, general relativity answers with infinite density and infinite curvature, while quantum mechanics answers with infinite energy fluctuations. In physics, an answer of infinity is not a solution. It is a violent warning flag that our theories have failed. To resolve this crisis, theoretical physicists have spent decades attempting to build a unified framework capable of harmonizing quantum uncertainty with gravitational geometry. The two leading theoretical candidates in this search are string theory and loop quantum gravity, both of which introduce radical revisions to how we view the fundamental constituents of reality. String theory proposes that the fundamental building blocks of the universe are not zero-dimensional point-like particles, but tiny, one-dimensional vibrating strands of energy called strings. Just as different vibrational modes of a violin string produce different musical notes, different vibrational patterns of a string produce different subatomic particles. One vibration manifests as an electron, another as a quark, another as a photon. Crucially, string theory naturally includes a quantum vibrational mode that corresponds precisely to a massless spin-2 particle, the graviton. Gravity is not added to string theory as an afterthought. It is an unavoidable mathematical consequence of the theory. However, for string theory's equations to function without internal mathematical anomalies, the universe must possess 10 or 11 dimensions, rather than the 4 we perceive. The extra spatial dimensions are hypothesized to be tightly curled or compactified into complex geometric shapes called Calabi-Yau manifolds at the Planck scale. While string theory provides an extraordinarily rich mathematical structure, it currently lacks any experimental confirmation, as its unique predictions occur at energy scales far beyond the reach of any particle collider humans could ever construct. The primary rival candidate, loop quantum gravity, approaches the problem from a completely different angle. Instead of trying to unify all forces into vibrating strings, loop quantum gravity focuses exclusively on quantizing space itself. It assumes that space is not a smooth backdrop, but is constructed from discrete, indivisible quantum loops woven together into a dynamic network called a spin network. In loop quantum gravity, space is not infinitely divisible. There exists an absolute minimum quantum of volume, roughly 1 Planck length cubed, and a minimum quantum of area. Space is granular, built like a flexible chainmail fabric. As a result, when matter collapses under gravity, it cannot collapse to a point of zero volume or infinite density, because space cannot be squeezed smaller than the minimum Planck volume. Instead of a catastrophic singularity, loop quantum gravity predicts that a collapsing star reaches a maximum quantum density and bounces back, replacing black hole singularities with exotic quantum stars, and the Big Bang with a big bounce. Despite the mathematical beauty of both string theory and loop quantum gravity, neither theory has yet produced a single verifiable experimental prediction that can be tested with modern technology. They remain brilliant theoretical frameworks floating in an experimental vacuum. Until a new generation of experiments or a revolutionary conceptual insight bridges this divide, the quantum gravity crisis remains an open wound at the heart of science. We are left holding two brilliant, hyper-accurate blueprints of reality that refuse to fit together, reminding us that our understanding of gravity, space, time and matter is still profoundly incomplete. Because the search for dark matter particles continues to return empty results in laboratory detectors, and because quantum gravity remains mathematically unresolved, a growing community of physicists has chosen to question a fundamental premise. What if dark matter is not an undiscovered physical substance at all? What if our basic understanding of gravity is simply incorrect at certain physical scales? Instead of inventing invisible ghost matter to explain why galaxies rotate too fast, perhaps we need to modify the laws of gravity themselves. This alternative scientific perspective is anchored by several competing hypotheses that challenge Einstein and Newton. The most prominent and historically successful of these alternatives is modified Newtonian dynamics, commonly known by its acronym MOND. Proposed in 1983 by the Israeli physicist Mordechai Milgrom, MOND offers a radical yet simple modification to classical gravitational laws. Milgrom noticed that the gravitational anomaly in galaxy rotation curves does not depend on the distance from the galactic center, nor does it depend on the total mass of the galaxy. Instead, the discrepancy appears at a precise physical threshold, when the gravitational acceleration drops below an extremely tiny value, approximately 1.2 times 10 to the negative 10th meters per second squared. In regions where gravitational acceleration is strong, such as inside our solar system, near stars, or on Earth, Newtonian mechanics and general relativity operate perfectly without any modification. But in regions where acceleration falls below this microscopic threshold, such as the distant outer edges of spiral galaxies, MOND proposes that gravity changes its behavior. At these ultra-low accelerations, the gravitational force no longer drops off according to the standard inverse square law, where force weakens with the square of the distance. Instead, the force drops off more slowly, decreasing linearly with distance. By altering the gravitational force law at extremely low accelerations, MOND explains the flat rotation curves of spiral galaxies with remarkable mathematical elegance, without requiring a single particle of dark matter. When astronomers plug a galaxy's visible light distribution directly into MOND's equations, the theory successfully predicts the precise rotation speeds of outer stars across hundreds of different spiral galaxies. Furthermore, MOND naturally accounts for the empirical baryonic-Tully-Fisher relation, a tight, observed correlation between a galaxy's total visible mass and its outer rotation velocity that dark matter models struggle to explain cleanly without complex tuning parameters. However, despite its impressive successes at the scale of individual spiral galaxies, MOND faces severe challenges when applied to larger cosmic structures. When physicists apply MOND to massive galaxy clusters, such as the Coma cluster or the famous Bullet cluster, the theory fails to account for all the observed gravitational pull. Even with MOND's modified gravity, galaxy clusters still require additional invisible mass to stay bound together. The Bullet cluster presents a particularly formidable challenge for MOND. The Bullet cluster consists of two galactic clusters that collided at high speeds. During the collision, the normal baryonic gas clouds, which make up most of the visible mass, interacted and slowed down due to electromagnetic drag, clumping near the collision center. However, gravitational lensing maps reveal that the vast majority of the cluster's mass passed straight through without slowing down, remaining situated far away from the visible gas. This spatial separation between visible matter and gravitational mass is easily explained by cold dark matter passing through the collision unhindered, but remains exceptionally difficult for MOND to accommodate without assuming the existence of undiscovered neutrino masses or residual dark matter. Recognizing the limitations of empirical modifications like MOND, other theoretical physicists have sought a deeper, more fundamental explanation for gravity's mysterious behavior. One of the most groundbreaking and controversial ideas in modern theoretical physics is the concept of emergent gravity, also known as thermodynamic gravity. Formulated most prominently in 2010 by the Dutch theoretical physicist Erik Verlinde, emergent gravity proposes a radical shift in perspective. Gravity is not a fundamental force of nature at all. It is not mediated by gravitons, nor is it a fundamental geometric property built into the fabric of reality. Instead, gravity is an emergent phenomenon, a macroscopic byproduct arising from the statistical interactions of microscopic quantum information stored on the boundaries of space. To understand what an emergent phenomenon is, consider temperature or elasticity. An individual atom does not possess a temperature. Temperature is an emergent property created by the average kinetic motion of trillions of colliding atoms. A single molecule of water is not wet. Wetness emerges only when countless water molecules interact collectively. Verlinde argues that gravity operates on the exact same principle. Drawing upon the holographic principle and black hole thermodynamics established by Stephen Hawking and Jacob Bekenstein, emergent gravity posits that space is a medium that encodes microscopic quantum information. When matter moves through space, it alters the distribution of this underlying information, changing the entropy of the system. According to the laws of thermodynamics, physical systems naturally evolve towards states of maximum entropy. What we perceive as a gravitational force pulling two masses together is actually an entropic force, a thermodynamic tendency driven by changes in quantum information density. Gravity, under this view, is simply thermodynamics operating at a cosmic scale. Crucially, Verlinde demonstrated that when you calculate the entropic forces arising from quantum information stored in an expanding universe, an extra gravitational effect naturally emerges at ultra-low accelerations. In regions where mass density is low and dark energy dominates, the elasticity of space creates an additional gravitational pull that mimics the exact effects of dark matter. In emergent gravity, dark matter is an illusion, an artifact created by the thermodynamic interplay between ordinary matter and dark energy. Beyond MOND and emergent gravity, other theoretical frameworks, such as tensor vector scalar theory or TeVeS and scalar tensor vector gravity, attempt to bridge these gaps by adding extra physical fields to Einstein's metric tensor. It is vital to emphasize that all of these alternative models remain highly controversial within the global scientific community. The mainstream consensus in modern astrophysics continues to favor the lambda-cold dark matter model because it provides a single, unified framework that successfully explains the cosmic microwave background, large-scale cosmic web structure, and galaxy cluster dynamics simultaneously. Yet the existence of theories like MOND and emergent gravity serves as a critical reminder of how scientific inquiry functions. Unproven hypotheses and competing mathematical models force us to remain objective and intellectually humble. They demonstrate that our current understanding of gravity is not a closed book but an evolving narrative where even our most cherished assumptions remain open to debate, testing, and potential revolution. Our journey across the vast landscape of physics reveals a profound truth. Gravity is the ultimate paradox of the cosmos. It is the weakest of all fundamental forces, yet it holds absolute dominion over the architecture of reality. From Newton's falling apple and Einstein's warped space-time fabric to the violent collisions of black holes, the invisible scaffolding of dark matter, and the quantum turmoil at the Planck scale, every breakthrough in our understanding of gravity has pushed human knowledge to new frontiers while uncovering deeper mysteries. As we stand at the edge of modern science, gravity remains an unsolved enigma, a silent, omnipresent architect reminding us that the universe still guards its deepest secrets, waiting for the next revolution in physics to illuminate the dark.